All right, so if we let f be a one-to-one function, and let's say we have a point on the inverse AB. So first of all, what can we say about the function f? If we have f inverse of A is equal to B, then I can say this is true. F of B is equal to A. So we'll use that fact a little bit later. So we're trying to figure out what we can say about the derivative of the inverse function at this point A. So let's draw a graph to illustrate this. So first I'm going to draw is this line y equals x, because if I have an inverse function, it'll be reflected over that line. So let's let this function be f. I'll try to draw a reflection of this over the line y equals x. So then this function right here is going to be f inverse. So we know a couple things, but really the same. We're saying the same thing in two different ways. Let's let this point right here be so let's let this point be BA. And I've drawn a tangent line to it. So let's represent the slope of that tangent line with this right triangle. We'll call this change in vertical displacement, that dy and dx. So now let's try to do the same thing on the inverse function. So this point here, if this point is BA, then this point must be AB. I can draw a tangent line to this point as well. Now let's think about what these rates of change are. Rates of change are as we reflect. So what we talked about in class, if I have a vertical line segment like this dy and reflect it over this line y equals x, that'll become a horizontal line segment. So this dy is actually reflected here. And for a similar reason, dx is reflected here. So now that we have all these geometric ideas laid out, let's see what we can say about this f inverse prime at this point A. So essentially what I'm asking for is, all right, looking at the inverse function, what is the slope of the tangent line at this point where the input to that inverse function is A? So when we're looking at the slope, remember we're looking at rise over run. So we're looking at the ratio of this vertical displacement to the horizontal displacement at that instant. So in this case, that's going to be dx dy. So let's start expressing, or just expressing this in different quantities. So dx dy, I can also say that is equal to 1 over this ratio dy dx. But keep in mind what dy dx was originally. That was equal to the derivative of the function f evaluated at the point B, at the x value of B. All right, so what I have here, I have f inverse prime of A is equal to f prime of B, which is true, but I'd really like to say something about that same input value. So I really want to express this, what I'm on the right-hand side of my equal sign in terms of the value A. So one thing I'll highlight here is that, remember that B is equal to f inverse of A. So the last thing I'll do here is re-express B as f inverse of A. And just to show the full inverse function theorem. So again, this comes in handy when you're trying to deal with derivatives for functions that you can't invert algebraically. We saw an example of this in class. You've probably seen a few examples of this in the web work. I hope this is a little more clear than my last shot at this. If you have any questions, just as always, let me know.